Next we will look into conversion from SR flip flop to D flip flop. So, here also for the since finally we want a D flip flop. So, we write down the operation for the D flip flop, that is if the D input is 0 and previous output is 0, then it is output Q p plus 1 should be 0. So, like that. Now, for S and R we write down the corresponding values that should come, like for 0 to 0 this S value should be equal to 0, R value can be do not care. From 1 to 0 S value should be 0 and R value should be 1, and from 0 to 1 S value should be equal to 1 and R value should be equal to 0. So, we have to be careful that we do not put 1 1 to the SR flip flop. That is why though I could have written an X here, but we do not do that, because that will be putting 1, that leads the chance that it will be putting 1 1 onto SR. Just to avoid that, so it is hard coded to 0. Similarly, from 0 to 1, so this is hard coded to 1 0 and this 0 is not a do not care. Okay. And this 1 1, so this is I can put this R value as 0 and S value as do not care. So, if you do a simplification and then we find that between S and R we need to put an inverter. So, S is equal to D and R equal to D bar. So, by putting this inverter, so we can get this SR flip flop converted to D flip flop. The vice versa, the other way, D to SR conversion. So, this is also similar, like what we do, we first write down the table for this SR, okay, and then for 0 0 can Q p equal to 0, then Q p plus 1 is also 0, 0 0, then Q p is 1, then the Q p plus 1 is 1. So, that way we make this table for this 1 1. So, this is invalid, and then because for SR we are not going to put 1 1 into it. So, they are kept as invalid. Now, we consider what should be the value of the D, like from 0 to 0. So, D is 0, from 1 to 1 D is 1, from 0 to 0 D is 0, it goes like this. Then for these invalid cases, since we are not going to apply this pattern, so they are taken as do not care. So, if we make it Carnot map and try to see what is the expression for D, and the expression for D becomes S plus R bar into Q n, basically this is Q p, this is somehow is not written properly, that is that S R bar S plus R bar Q b. So, R is inverted, Q p is taken, they are ANDed here and they are ORed with S, and that is fed to the D flip flop. So, this way we can make conversion from D flip flop to SR flip flop. JK to T conversion. So, we already know that for JK, if we try these J and K inputs together, so it will give me a T flip flop. So, why does it happen like this? For T, the behavior expected is if the T value is 0, output will not change. If the T value is 1, output will toggle. Okay. So, for 0, if the previous value is 0, the next value is also 0. Similarly, if the previous value is 1, the next value is 1. Whereas, for if the T input is 1, so this Q value is if it was 0, now it will become 1, and if it is 1, now it will become 0. If the T is 1, if the Q p is 1, then it will become 0. Now, for this JK, what happens is that we have got this. So, for the JK, so if we want to get this type of behavior, then for 0 0 this J input must be equal to 0, K input can be do not care. For 1 1, K input must be equal to 0, because this J input being 1 will set it to 1, J input will being 0, it will maintain the previous value. So, in both the cases the value will be equal, Q p plus 1 will be equal to 1. Similarly, here, so if we are trying to get from 0 to 1, so J input must be made equal to 1, K input is do not care. So, if K input is 0, by virtue of J equal to 1, so it will set the flip flop to 1. If K equal to 1, by virtue of toggling property of JK flip flop, it will toggle from 0 to 1. So, in either case, so this value will become equal to 1. And for 1 0, so this J input can be do not care, K input is equal to 1. So, it will be resetting the flip flop to 0. Now, if we draw the Carnot map and then we see that minimize it, then it turns out that J equal to T and K equal to T. So, both the cases, so this T input should be connected to both J and K. So, that is the tying of this J and K inputs together and calling it as the T input. So, this way you can convert one J K flip flop to T flip flop. So, here is again another exercise that says that how can you how this circuit will behave when you will be when you will set this behavior of this circuit. Now, for that matter, so you can do it like this. First of all, you can try to get what is the value of D here. So, D, so your S signal is low here. So, as long as S is, so let us say this is a 0 and this is 1. So, when S is low, A 0 is selected, when S is 1, A 1 is selected. So, for this much time, this D input is high, and at this point it is becoming low, and then it is becoming it will remain low for this time, then A 1 is becoming high. Okay. So, it continues like this, then S is becoming low. So, A 0 will get selected, but A 0 is high here. So, it will continue like this, and then at this time it will be coming down, and then S is high, S is low, for this much time it will be like this. Then this A 1 is high here. So, A 1 is high here, A 1 gets selected, and then S is becoming low here, and at this time you see that A 0 is also low. So, A 0 is low, so it will come down, and then it will continue like this. Then at this point it will be A 0 is becoming high. So, it will become high. Now, again at this point S is becoming high. So, A 1 will get selected, A 1 is high. So, at this point it will come down, and then it will continue like this, and then S is becoming low and A 0 is high. So, it will go like this. So, this is the behavior of the D line. Now, from this behavior, so you can very easily draw the Q line behavior for the D flip flop. So, because at this point your this Q is high. So, this will be high, and then at this clock edges basically you have to see. So, this is high, then again at this clock edge it is low. So, it will be coming down here, and then again at this clock edge it is high. So, it will be going high. Next clock edge the signal is low, D signal D is low. So, it will be, so this way you can draw the rest of the part. So, if for any sequential circuit tracing, so first you determine the value at the input of the flip flops, and then based on the clock you just try to draw it. So, that is the technique for doing it. So, this is another example where this Q bar line has been fed back to D. Now, see this so this clock is initially so Q bar line is initially high. So, and Q line is initially low. So, you can say that the D line is initially high. Okay. Now, since this is a D flip flop, then this Q bar line is fed back. So, this so this Q value, so this is getting a high at the D. So, at the clock edge, so this value will be going up. Then and as soon as this goes up, so this goes down. Okay. Then it continues like this till the next clock. Now, at the next clock, what is the value of D? So, that is equal to the value of Q bar. Okay. So, this whenever this Q bar has become low, this D value has also become low. So, at this point this Q bar value is low. So, D value is low, and this the Q will be coming down because it is coming as low here. So, it will be coming down, and that it will continue for this much of time, and this then this Q bar line. So, that is the complement of this thing Q, it will continue till this, and D line, since it is equal to Q bar, it will go like this. So, this way you can draw the circuit, you can draw the timing diagram and complete the portion. So, I am leaving it for you for a practice. Next, we will be looking into another sequential element which is known as resistor. So far we have seen flip flops, and in a flip flop you can say that we can store only one bit of information. If the clock signal is not given, then if I have got a D type of flip flop, then it will remember what was the last value of the D given to it. So, that is why it may be considered as a 1 bit register. Now, if I want to remember multiple bits, okay, so instead of a single bit, if I want to remember multiple bits, then what is needed to be done is that we should have more than one D flip flop. So, we should have a collection of 2 or more D flip flops with a common clock, and this type of structures they are known as registers. So, registers are often used to store a collection of related bits, for example, a byte of data in a computer. So, like here this particular structure you see it we have got 4 D flip flops and the clock signal is common to all of them. So, at the positive edge of the clock whatever value is coming on to in 1 will be stored into the first flip flop. Similarly, whatever coming in 2 will be coming in the second flip flop, in 3 will come in the third flip flop, and in 4 will come to the fourth flip flop. So, I can say that on the positive edge of the clock the 4 bit pattern that I am giving here will be stored in these flip flops and they will be available on these outlines. And also there is a common clear line connected to all of them, all the flip flops they are connected using this clear line. If the clear is equal to, if clear is set or is active, then all the flip flops will content will be cleared. There may be some preset control lines also that is not shown in this diagram. So, that may preset all the flip flops to 1. So, these type of structures are very common inside computers and they are known as the registers. So, next we will be looking into this construction of these registers using these flip flops. So, this is a standard 4 bit register IC 74175. So, there are 4 bit means there should be 4 such flip flops inside, and each flip flop has got one D input and one Q output, one Q bar output, fine. So, it is written as 1 D, 1 Q, 1 Q, and there is a bubble shown here, that means the pin number 2 is the Q line and pin number 3 is the Q bar line for flip flop 1. Similarly, this 2 D means this is the D line for the second flip flop pin number 5 and its outputs are 2 Q and 2 Q bar. So, it is second flip flop's Q line is 7 and Q bar line is 6. So, this way this chip is there and this clear and clock. So, these are common for all the flip flops. If the clear signal is made 0, so all the Q values will be made equal to 0 and Q bar lines will be made equal to 1. And then this the clock signal is required because, and this symbol shows that it is a positive edge triggered flip flop. So, internal diagram is like this. So, we have got this 4 flip flops, okay, and these individual flip flops. So, they are having this D flip this D line, clock line and the clear line, and there are outputs like Q and Q bar. So, this way. So, this standard 4 bit register IC is there. So, we can use it for design. We can have 74273, this is another IC, another integrated circuit chip where we have got this 8 such flip flops. So, 1 D, 2 D, 3 D, 4 D and then this 1 Q, 2 Q. So, interestingly you see that Q bar lines are not taken out. Okay. So, Q bar lines are not taken out because for a D flip flop. So, if you put both Q and Q bar line for 8 D flip flops, so we will be needing how many pins. Okay. So, each flip flop requires 3 pins, 1 D, 1 Q and 1 Q bar. So, 3 into 8. So, 24 pins will be needed there itself, plus there is a supply voltage VCC. So, that is 1 pin, then the ground pin, ground line. So, that will be 1 pin. And this clock and clear. So, there are 2 more pins. So, 24 plus 4 28 pin, but this 74273 it has got lesser than 28 pins. So, this is you can see here up to pin number 19. So, 1 2 3 4 5 6 7 8 9 10 and 10 is not shown here, 10 is actually the supply line, the VCC line, and there is another ground line. So, total it will have 20 pins in it. So, to fit the design into 20 pins, so what has been done, the Q bar lines have been cut. So, Q bar lines are not provided. So, if externally you really need the Q bar line in your design, so you can put an inverter and do it. So, what I mean is that so you have got this D line and this Q line. So, Q bar pins are not taken out. So, if you need externally the Q bar, so put an inverter here and take the Q bar from there. Okay. But in most of the cases, so we do not need both Q and Q bar lines. So, that is why it is many chips will not have this explicit Q bar lines in them. Some of the registers, they have got 3 state outputs. So, 3 state output means that the output can be 0, it can be 1, or it can be in a high impedance state, that is neither 0 nor 1. So, it is like this. So, there is an enable line. So, if this enable line is active, that is enable line is 0, then only this whatever be the state in the register. So, they will be available on this 8-bit line. So, there is 8-bit input and 8-bit output. So, whatever be the 8-bit value that you are giving here, that is stored into this flip flop, but that is not immediately visible at the Q output. For getting the output here, so you have to make enable equal to 0, then only they will be visible. So, this type of gates, so they are known as tri-state gates. So, these tri-state gates are enabled by means of this enable pin. So, if this enable line is 0, then these tri-state gates are enabled. As a result, these Q outputs are visible at the output of the tri-state gate. So, this helps us in connecting a number of register outputs together. Okay. So, like this 74374. So, this is a chip where we have got two controls. So, one is our clock, that is the standard clock, and there is another pin which is known as output enable or OE bar line. So, if you look into this logic diagram, so it shows that the OE bar line, so this is connected to these tri-state buffers. So, if this OE bar line is 0, then this will become equal to 1. As a result, all these tri-state buffers will be enabled, and the value that is available at Q will be coming to the pin number 2, which is corresponding to the 1 Q line. Similarly, this Q output will be available at pin number 5, which corresponds to the 2 Q line. So, this way we can have this 8-bit register with 3 state outputs. So, once apart from this logic high and logic low output, so it has got an high impedance state, which is neither logic 0 nor logic 1, and it is useful while you are connecting a number of such devices together. Like what I mean is that, suppose I have got 2 registers like this, and these 2 registers outputs, they are fed to another register. So, this output is one 8-bit output. So, this output is also another 8-bit output, and both of them are feeding to this register. So, this is R1 and R2 and R3. Now, if I do not have this type of tri-stating facility, then one way to do it is that I have got this R1, R2, and then I put some multiplexer type of structure, the 8-bit multiplexer, where this 2 comes, and then they finally go to R3. All these lines are 8-bit, that is this multiplexer is consisting of 8 such 2 to 1 multiplexers. Fine. Now, I have to have a select line by which I have to select which multiplexer output I want to go to R3. But if I have this type of tri-state facility, then what I can do, I have this R1 and R2, and their outputs are tri-stated, and then I can, if I enable this R1 register, okay, then this if I give enable signal to this or this OE signal, the output enable signal to this R1 register, and I do not give the OE signal to R2 register, then R1's content will be coming here. Similarly, if we do not give OE signal to this and give the OE signal to R2, okay, if we give OE signal to R2, then this value will be coming through R3 like this. So, I do not need to put separate multiplexers if my registers are tri-state buffers are having tri-state buffers in them. So, that is their outputs are tri-stated. So, that is why in a computer design. So, while we have got a number of registers and their outputs are made to be common. So, we take help of these tri-state registers, and then there is a controller that we have in the computer system. So, that will be controlling this output enable lines, and it will it will determine like which registers output will be going to which register. So, we do not need separate multiplexers for them, that reduces the overhead. We can have registers with clock enable, like so. So, we have got here this clock, and clock enable is often called load or the gated clock. So, this is this load signal is given. So, here the clock signal is given, but until and unless this load signal is also given, the value that is coming on this D will not be stored into this register. Okay. So, this design is shown here. So, you see if this clock enable is equal to 0, if the clock enable line is equal to 0, then whatever is output out 0, so that is circulated back into the D flip flop. So, for loading something onto this D flip flop, I must make this this CE line equal to 1 or the load line equal to 1. Then what will happen, if this line is equal to 1, then this IN 0 will be coming here. So, this IN 0 will be input 0 will be stored into this D flip flop. Similarly, this IN 1 will be coming onto this line, and this will be stored into this D flip flop. I am sorry, there is a shifting in this zeros and ones. So, this 0 is with this input and this 1 is with this input. So, they are actually identifying which input will be selected if C is equal to 0. So, C equal to 0, out 0 is selected, if C equal to 1, in 0 is selected. Similarly, if C equal to 0, out 1 is selected in this case, and in 1 is selected if C equal to 1. So, this way apart from this clock and everything, we can have another control, which is the load control. So, this load control will tell when the value should be loaded into the register when the next clock comes. Like if the load is low, even if the clock signal is there, the value is not loaded. And there is a clear, of course, that if the clear line is 0, then the register will be cleared. So, that is there. And in this particular case, we do not have the tri-state buffering shown here. There can be an OE bar control also, output enable control also in the general case. So, normally in a register we will have the clock input, the clear input, and we will have this load input and the OE bar, the output enable line. So, all those lines can be there. So, this is one chip 74377. So, that has got that is an 8-bit register with clock enable. So, clock enable, it is some sort of, you can say it is a gated clock type of structure, as if this clock signal is given, but if this enable line is low, if the enable line is high, in that case. So, this line, this point is 0, as a result this point it is 1, and then this Q line will be circulated here and it will be put into this D flip flop, into D input. Otherwise, if this enable line is low, okay, so this is 1, so this is 0, as a result this output is 0, but this is this was equal to 1. So, whatever be this D input will be coming through this AND gate and through this OR gate, it will finally reach this D input, and that will be stored into this D flip flop. So, this shows the structure of this clock enable circuitry. So, we can have this enable and this clock. So, this extra part that we have put here, that is like a multiplexer type of structure, that is useful for selecting whether I am going to circulate the previous value because enable line was not active, or I am loading a new value because the enable line is active. So, this shows a typical diagram, like normally in an application that involves data transfer, which is very common in case of computer systems or the processors. So, we have got a bus, and from this bus a number of registers are connected. Okay. So, these A, B, C, D, G and H. So, these are a few registers, and each register, so they are connected to the same bus. Okay. And what we want is that they should be able to communicate between themselves, like one register content I should be able to transfer to some other register. Now, suppose I want to transfer the control of register A to register G. Now, how can I do this? So, for that purpose I have to enable this register output, okay, and I have to enable the load signal for this G register. So, this enable A and load G. So, these two inputs are to be given, and accordingly it will be doing the transfer from A to G. Similarly, if I want to make a transfer from A to H, then this load enable A should be given and this load H signal should be given. So, in a very simplistic situation, so it may be the case that I have got these 4 registers A, B, C, D, from where we want to make transfer to these registers G and H. So, I can have some sort of decoder where this E and F they come as control, and they will say from which register the transfer will take place, and only one of the, since this is a decoder, only one of these outputs will be made equal to 0. So, as a result only one of these registers enable line will be enable line will be active, and this 8 bit will be coming from that register. Other registers those output, all the outputs are tri-stated. So, they will not affect the bus. Once the content is available in the bus, then it is assumed that some other controller it will provide this either this load G signal or load H signal to load the value onto the proper register. So, this way we can have this registers implemented, a register data transfer implemented by means of individual registers that has got enable and load lines in it. Another class of registers, so they are known as shift registers. So, in shift register it is a register that stores input values in sequence. So, at each clock tick the values stored are shifted from one flip flop to the adjacent flip flop. So, so there is a serial input. So, problem with this previous structure is that if you are trying to store some value onto these registers, so I have to give 8 bit parallel lines, but often getting so many parallel lines from somewhere is difficult. So, we want to transfer them, we want to transfer the data serially, and that way we have got only. So, this may be some higher number of higher size register, maybe 8 bit register or 16 bit register, whatever, but I am not feeding all those registers simultaneously with external data inputs. They are coming through this serial input line, and the serial input line. So, it affects only the first D flip flop, and this first D flip flop's Q output is connected to the D input of the next flip flop, and it continues like that. This Q output is connected to the next flip flop's D input. So, it continues like this. So, this way with the when the clock pulse comes, then this serial input data it gets loaded into this D flip flop, and the previous value of this D flip flop is transferred to this next flip flop. So, this way this acts as a serial chain. So, this type of registers, so they are known as serial input serial output register, shift register, or SISO register, serial input serial output registers. And with the individual clock pulse, so one bit data is shifted from this SI input into the first register, and 1 bit of data from the last register is shifted out. So, this is the serial input serial output type of shift register structure.